Hi, welcome to part 2 of equilibrium, or as I like to write it, equilibrium with a K because that's the constant for equilibrium. If you notice, these are some of the vocabulary words we looked at last time, where there's reactants, products, a law of mass action. A law of mass action, you write an equilibrium expression or a mass action expression. Equilibrium is the state where the concentration of the reactants and the products are constant with time. In other words, as reactants react and produce products, the products also have a chance to form reactants, and this is happening at the same rate. And this happens in a closed system, which is something a little bit different than what you and I are used to with an open system. And these are the values, different types of Ks that are listed. And if you need to have clarification on any of this, you can go back to equilibrium part 1. So let's just review some basic equilibrium questions first. And the key term here is that this states that it's at equilibrium. Okay? And at equilibrium, it's 25 degrees Celsius, and what's not listed here is that we're going to find the equilibrium constant. If you notice, these are molarities. And since they're molarities, we're going to find something called Kc. And Kc goes with molarity. So, to do this, I need to write an equilibrium expression, or a law of mass action expression. And that is to start with the products, and these are the reactants. And Kc, like any K, is the relationship of the products to the reactants. So, what we're going to do is we're going to start with our products, and we're going to write SO3, and we're going to go ahead and put brackets, because when we have brackets for molarity, that is in terms of Kc. Kc uses brackets. And we're going to go ahead and put a 2 here. You know, actually I'm going to move this over and put it over here so we actually have some more room to do our math. So I'm going to write SO3 with brackets signifying I have molarity. And I'm going to square it. Remember that exponent? The coefficient became an exponent. Now, my line is just like my arrows here. And I'm going to go ahead and use oxygen first. It doesn't matter, but since you're going in order from products to the reactants, you might as well go ahead and use this order. That's O2 in brackets. I'm going to multiply them together and have SO2, sulfur dioxide, squared. Now, that right there is my law of mass action expression, my equilibrium expression, and as you can see it right now, those are my directions. It's happening at 25 degrees Celsius. That's something informational. I don't need that for this type of problem that we're doing right now, though. And I'm going to go ahead and I'm going to take these values right here because these are the values at equilibrium. And that's what this is. Remember, we wrote a law of mass action and equilibrium expression. So I simply take these values and plug them in to my equation. And so what do I have? I have for SO2, I have 0.05 molar. Okay, and what am I going to do with that? I'm going to square it. And you can do it any way you want to. I'm going to go ahead and start from the top. I'm done with that one. O2, I have 0.04 molar. And that goes in the bottom of my fraction, my expression. And on the top, I'm going to go ahead and put 0.02 molar. And I'm going to square that because those are my directions. So if I do that, I'm going to find the value for Kc at 25 degrees Celsius for this specific equation. And when I do my math, I actually come up with a value of 4. So solving this equation right here with these values, I come up with a value of 4. And that 4 is equal to Kc. And if you recall, last class we talked that if a value of an equilibrium expression is greater than 1, then at equilibrium you have more products than reactants. Again, go back to the previous video, equilibrium 1, if you need help. So my key to this is that these molarities are values at equilibrium. And so we're going to call this Chem 1 baby. Let's look at a different problem. All right, now what is this problem here? In this problem, they give me the value of K. Kc equals 4, which makes sense because at 25 degrees Celsius, what we just did on the last page, we just found the Kc to be equal to 4. What do they want to know here? Well, they give you as the values at equilibrium. Those are key words that this is going to be a basic type of problem, a Chem 1 baby problem. They give me the values for SO2 and the values for O2, but we do not know, this is our question mark right here, we don't know our values for SO3, sulfur trioxide. So they want us to find the molarity. Well, what do we know how to do? We know how to write an equilibrium expression. And so, just like we did on the previous page, the equilibrium expression is still the products over the reactants. I'm going to go ahead and write the same thing I wrote on the other page. I'm using brackets because I have molarity. Okay, and then I'm going to go ahead and put O2 here, and sulfur dioxide here, and I'm going to square it because that's what my reaction tells me to do. And now what do I know? I know that my Kc is equal to 4. Okay, and actually let me move this down because I didn't do that very well on the other page. I know that my Kc is equal to 4. Okay? My sulfur trioxide, I don't know, do I? I don't know this. So this is my x. So I'm going to put x up here, and what do I do with x? Well, my directions, my law of mass action, my equilibrium expression, tells me that I need to go ahead and square it. Putting my values in according to what is in my chart, I have oxygen is O2 molar, 0.02 molar, and my sulfur dioxide is 0.03. And if you recall, the units for Kc and Kp, we don't have any units. Okay, even though there's units for every single reaction and every single expression, they're also different. It's too confusing. So we just go ahead and agree not to have units. It's just a ratio of products to reactants. Now, if I solve this, I'm going to take 0.02 times 0.03 squared, solve that, and I'm going to go ahead and do 4 times 0.02 and 0.03 squared, and that's going to be equal to x squared. Make sense? So that's going to give me a value of, I'm running out of room and write it up here, 0.0004, and that is equal to x squared. So to solve for x, I'm simply going to square root that. So I'll square root this, which makes that squared go away. And the square root of x, if I actually solve this, is equal to 0.02. So my molarity for SO3 at equilibrium is 0.02 molar. That's what SO3 is at equilibrium. That's the value. And that's how you do it. Now, if you notice, in these two types of problems, we've seen right here the terms at equilibrium. And in this problem right here, we've seen the term at equilibrium. Let's come over here and look at a new type of problem. Oh. And right here, it says, calculate the equilibrium concentrations. So here I'm going to go ahead and I'll go ahead and highlight this. Calculate the equilibrium concentrations. I don't know them. Before, we knew the equilibrium concentrations. Now we don't. So that makes this different. That makes this a different type of problem. It's a more advanced. And we're not going to call this Chem 1 baby. We're going to call this ice. And ice, I stands for initial. So use the initial concentration. C stands for the change, and E stands for the equilibrium value. So that's what the ICE stands for. So let's look for them. And to do this process, I'm going to put actually let me use a different color, sorry. I'm going to match it to what's on the other page. ICE E. So our job right now is to find the initial concentrations and find out what in the world they're trying to ask us. Well, we just highlighted, calculate the equilibrium concentration of each species. What the heck is each species? What's that mean, each species? Well, these are all the species. H2 is a species, CO2 is a species, H2O is a species, and CO is a species. Those are the 4 different elements that are in our reaction. What else do we know? We know that 1.0 moles of carbon monoxide gas and 1.0 moles of water vapor are placed in a 1-liter flask. So we know that, don't we? We know this is true. Now, what we need to do is we need to deal with molarity. Okay? So I know when I have this, I know I don't have any equilibrium concentrations, and so that's how I know I'm doing an ice problem. I know that I have 1.00 moles of carbon monoxide in a 1-liter flask. I also know that I have 1.00 moles of water vapor, that's water gas, in a 1.00 liter flask. If you notice in this problem, there's nothing at all listed about carbon dioxide or hydrogen gas at the beginning. In other words, they're not there. So the 2 reactants, carbon monoxide and water vapor, are placed into a flask. You do know something else. You know that the Kc is 5.10 at 700 degrees Kelvin, or excuse me, 700 Kelvin, I shouldn't say degrees. So I know that I have a Kc value. I may or may not need that. So let's see what is going to happen here. What's going to happen? My reactants are right here, aren't they? These are my reactants. They're going to react. Okay? So if they react, what's going to happen to them? Well, if you notice up front, they're coefficients. For every 1 mole of this, you need 1 mole of this to make 1 mole of this and 1 mole of this. So what do I know? I know that this is going to go down, and this is going to go down by how much? Well, by a value of x, or I could say 1x if I wanted to. Go back here. And these are going to go up by a value of 1x. Do you agree with me that as the reactants react, they produce products? And they're going to go down by a certain amount. How much? Well, I don't know. But they're going to go down with a ratio of a 1 to 1 to 1 to 1 relationship. And those are written out front. We just don't normally write them. So if that's true, and by the way, why in the world did I put 1 mole of carbon monoxide gas over 1 liter right here? Why did I do that? That's because I need things in terms of molarity. How do I know that? Because my Kc is in terms of molarity, isn't it? Okay. So if that's true, what is my value here? My value is 1.00 molar, isn't it? You know what the answer to this is? This is 1.00 molar. And this is also equal to 1.00 molar if I do my math. But what happened to the 1.00 molar? It changed. What did it change by? It changed by x. These both went down by x because I started with 1 molarity for each of them, but part of what was present reacted. What happened to that? Well, it formed carbon dioxide and hydrogen gas. How much, I don't know yet. So if you see here, this is exactly what we did on the other page. I have 1.00 molar starting for both carbon monoxide and water, both of my reactants. They went down by x. Carbon dioxide and water vapor went up by x. And our job in this is to find the equilibrium concentrations for all the species. Well, do we have that? I think we do. If you look, these are the equilibrium concentrations, but I have a problem. Their values are in terms of x, and I have no idea what x is. But we do have a Kc value, don't we? We know that. And we know how to write an equilibrium expression. So let's go ahead and do that. I'm going to write an equilibrium expression. Kc, ooh, that's kind of big. And I'm writing with a highlighter, that's why. And by the way, before we start, let's just go back for a second and look. Our Kc is 5.10, right? So I'm going to go ahead and write Kc, which is equal to 5.10, is equal to H2, and I know I'm using molarity, so I'm going to put brackets, times CO2 divided by H2O and CO. That's my law of mass action. Now, what do I need to plug into those? Then those brackets needs to go to the values at equilibrium. Well, what are they? Well, if you look, these are my values. So for H2, my value is x. For carbon dioxide, my value is also x. See where I'm getting those from? And for H2O, my value is 1.00 minus x. And for my value of carbon monoxide, it's also 1.00 minus x. See how that happened? So what I'm going to do right now is I'm going to erase these down here so I have a little more room. So all I do is take those equilibrium values and plug them into my law of mass action, my expression that tells me that at equilibrium that's what's happening. So now what's going to happen? Well, what do I have here? I have x squared over 1.00 minus x squared, don't I? And that is equal to 5.10. Now how in the world am I going to get rid of those x squared? I could do the quadratic formula, I can do all kinds of things. But let's think algebraically, and all I need to do is take the square root. So if I square root this whole thing, what's going to happen? That means that I have the square root of 5.10 equal to x over 1.00 minus x, don't I? How about that? And if I do my math, I'm going to take the square root of 5.0, and actually let me do that on my calculator here. So that we can actually get a number value. And if I do that, let me write it over here. I'm going to go ahead and have 2.26. And I'm going to multiply that by 1.00 minus x. And that's going to get me equal to x, if I do my math. So, if I do my algebra, I have 2.26 times 1, which gives me 2.26, minus 2.26x equals x. Now if I do math here, I'm going to have 2.26 equals 3.26x. Right, if you move this over to this side, you have to add it on both sides. And then I'm going to have, simply solving for x, 2.26 divided by 3.26. And that's going to give me 0.69. And remember, this is in terms of molarity. So that's what x is. Okay, because I'm solving for x. So, what have I done? I've solved for x, haven't I? That's 0.69 molar. Now, what did that give me? Where am I at in my problem? If you look at this for a second, it said to find to find or to calculate the equilibrium concentrations of each species. Well, that's what this is right here, isn't it? Isn't this the equilibrium concentrations of each species? Except I still don't really know what they are. Or do I? Oh wait, we found X on this page. We found out that X was 0.69 molar. So that means we can plug this in. That means that at equilibrium, this is 0.69 molar, because that's what X is. And the equilibrium, this is 0.69 molar. Now how would I do this? Well, you're going to take 1.00 minus 0.69, and the same thing here, 1.00 minus 0.69, and the molarity here, when you do that math, gives you 0.31 molar. 0.31 molar. And so that is how you solve that problem for the equilibrium concentration. Let's solve a different problem. Here it says to calculate the value of the equilibrium constant. Okay, that means they want us to find K. We don't know K. Now what kind of K is this? Is this Kc or Kp? Well, if you look, you have moles here, and you have liters. So that means we're finding Kc. So, let's look and see what we have going on. Do we have anything about concentrations at equilibrium? If you read it, it says, initially, so for starters, a 1 liter flask filled with 2 moles of sulfur dioxide and 2 moles of nitrogen dioxide gas was heated and allowed to reach equilibrium. So if you read that very first sentence, you can look and see that it is not at equilibrium, it's allowed to reach equilibrium. And that didn't work, did it? Because that was a pen. So, sorry, let's highlight and let's use yellow. It's allowed to reach equilibrium, so it's not at equilibrium. That means we're going to use ice. Okay? And so if we use ice, I'm going to go ahead and put ICE out to the side here. Come on. Oh, goodness. I'm just not having a good day here. So I'm going to go ahead and do this. ICE, initial change in equilibrium. And let's see what they are asking me to do. Find the value of equilibrium constant. That means that for sulfur dioxide, which is sulfur dioxide right here, I have 2.00 moles in a 1 liter flask. That's going to give me a molarity of 2.00 molar. What about nitrogen dioxide? That's here. What do I have? I have 2.000 moles in 1.00 liter. That's going to give me a 2.000 molar solution, or gas concentration. Now, does it say anything at all about SO3, sulfur trioxide, or nitrogen monoxide? Nope. That means when you start, there is nothing here, because initially only these two reactants are in the container. Now it's heated. That's what our problem tells us, and it's allowed to reach equilibrium. Another key here is that it's not at equilibrium is it says after equilibrium was achieved. So you know for a second fact here that it's not at equilibrium. All right, so I'm going to go ahead and erase this to the side here. And we're going to go ahead and do our problem. So let's proceed for a second. What's going on? Well, this is going down. How do we know that? Because these are reactants, and there's reactants present, and they're going down by X because there's a 1 out in front of each of them, isn't there? And these are going to go up because there's nothing there to start with, and reactants react to produce products, and they're going to go up by X also. I'm going to leave out the 1 since it's just 1X. What happens now? That means at the end here, X is present for sulfur trioxide and nitrogen monoxide. And what's true over here? Well, these are both going down by X, and they both start at 2 molar. This is a little more accurate in its measurement, but that's the bottom line. Now let's think about it for a second. What's going on? Well, if I look what else do I know in my equation? Because I sure can't solve for Kc right now. I can't find the value of the equilibrium constant. I don't know what x is. So they must be giving me some more information. So if you look, they tell me that the concentration of NO after equilibrium was achieved is 1.30 moles. Well, let's change that into molarity. So 1.30 moles divided by 1.00 liters. Why is that? Well, we're still in the same flask, aren't we? That's going to be 1.30 molar. And when is that? Oh, that's after equilibrium was achieved. So after equilibrium was achieved, nitrogen monoxide is equal to 1.30 molar. I know that. So let's look and see what happens. Sorry. Let's just, well, we'll copy this, okay? Sorry. So before I even do anything right now, I don't need to do ice because I did that on the other page, but I do need to know my equilibrium values, right? And so that's 2.0 molar minus x, 2.0 molar minus x. So I'm going to go ahead and copy those down here. I'm just not having a good day with this flipping stuff. So I'm going to go ahead and say that this is E for equilibrium. And I know that this was 2.0 molar minus x. This is 2.00 molar minus x. This was x and this was x. And we knew that this was 1.30 molar. Now, if we know that x is equal to 1.30 molar, don't we know that this is also equal to 1.30 molar? And can't we find the molarity equilibrium for both of these? You take 2.0 minus 1.30 and 2.0 minus 1.30, and you get the molarity. And if you do that, this is 0.7 molar, and this is 0.7 molar. So what's true? Don't we know the molarity at equilibrium for every single one of these species? Should be a double arrow here. And what did they want us to find? Oh, they wanted us to find the value of Kc. So how do you do that? If you said write an equilibrium expression, you are correct. So, sorry. I'm going to go ahead and write that. Kc equals SO3 in brackets, because it's molarity, times NO over NO2 and SO2. Now those are my directions. I'm going to go ahead and plug my values in. My values are 1.30, and leave the molarity out, 1.30, because my Kc doesn't have any units. And I'm going to put in 0.7 and 0.7. And if I do my math, I come up with Kc equaling 3.4, which means at equilibrium I have more products than reactants because my K is greater than 1. All right, let's try one more. Now, in this problem, we're going to find the value of Kp. What do we know? And if we have Kp, shouldn't we have atmospheres? Oh, look, we do. So let's look and see what kind of problem this is. If it's a Chem 1 baby, let's look for our clues. S8 is introduced into an empty container. So it's an empty container. That means that it's empty. There's nothing in there at all. Duh. All right. The starting pressure is 1 atmosphere. There's a clue right now. Is this at equilibrium? No. It's got a starting pressure. And the starting pressure, let's go through and write our information down, of S8 is 1.0 atmospheres. Atmospheres. How do we know that? Because it says S8 is introduced, right? It's introduced in my container. So S8 is introduced into my empty container, and the starting pressure is 1 atmosphere. So that's my I. Is there any S2 present at the starting point? No, because it's empty at first, and then S8 is introduced. So I know that I have nothing here. So now what's going to happen? Well, it says after decomposition took place, according to this decomposition reaction, what is true? This is where I do my C for my change. This is going to go down by x because there's a 1 out here. What's this going to go up by? Oh, look, there's a 4 out here. So that means it's going to go up by 4x because this is a 1 to 4 relationship. So there's my I, my initial. 1 atmosphere of S8 is introduced. No atmospheres of S2 is present. My change, S8 is going down by x because there's a 1. My S2 is going up by 4x because there's a 4 out front, and it's a product, and there's nothing there, so it's going to be produced. And now I want to find my E for equilibrium. Well, what is true? Here I have 1.0 atmosphere minus x, right? And what do I know here? I have 4x at equilibrium. Let's look and see what else we know. After decomposition took place, according to the following reaction, the partial pressure of S8 was measured at 0.25 atmospheres. Okay, so we know that S8, right here, at equilibrium, actually has a value. It's 0.25 atmospheres. So that means after that 1 atmosphere went down, there's 0.25 atmospheres left. And they want us to find the value of Kp. So how do we do that? Remember, this is equal to 0.25 atmospheres. Okay, so over to the side here, I'm going to say Kp is equal to the pressure of S2 in parentheses to the 4th. Now why am I doing this? Because I'm finding Kp. And Kp is in terms of atmospheres, and so that's how you delineate that you're using atmospheres. You use parentheses and P of whatever your species is. All right. I'm going to do pressure of S8, and that's my law of mass action expression, my equilibrium expression, and now I need to plug my values in. So be careful, because my value for S8 at equilibrium is 0.25 atmospheres. You see that? It's 0.25 atmospheres. They tell me in this problem that the partial pressure, right, after decomposition took place, okay, what's left is 0.25 atmospheres. And that problem should actually read at equilibrium, but it doesn't, but that's assumed that you understand that. So that's what I put down here for PS8, the pressure of S8. Question, what is x? Well, if you solve for x, don't you get 0.75, right? 1.00 minus x equals 0.25. Solving for x, you get 0.75 is equal to x. If that is true, then you can take 4 times 0.75, and that gives you the value at equilibrium for S2. 4 times 0.75 is 3. Now, what do I need to do with that? I need to take that to the 4th power. Okay, and I don't mean to confuse you by putting that in a different color. And if you take 3 to the 4th and divide it by 0.25, you come up with 3.2 times 10 to the 2nd. And that is equal to Kp at 1325 Kelvin. Okay, and again, that's a number that's greater than 1. Kp is greater than 1, so that means at equilibrium you have more products than reactants. Let's try one more. And actually it's not one more, it's a twist on this. Same problem. It's to find the value of Kc. So what was Kc again? We just found Kp. And Kp that we found was 3.2 times 10 to the 2 at 1325 Kelvin. They want us to find the value of Kc, which is in terms of molarity. Right? This is in terms of atmospheres. Okay? So we want to find it in terms of molarity. We just found it in terms of atmospheres. And so here's our conversion to change it. So let's look and see what this means. That means if we know Kp, it's equal to the value of Kc times R and T multiplied together to the power of delta N. What the heck is that? Well, R is a universal gas loss constant. You may or may not remember that from gas laws. It's 0.08206 liter atmosphere mole Kelvin. Okay, that's the gas loss constant. Pi is 3.14. R is 0.08206. And to do delta N, you're going to take the coefficients in the equation, and you're going to take the products minus the reactants, and that tells you the change in moles, right? Final minus initial. So let's do this. Let's plug it in. But let's be smart about it math-wise, and we're solving for Kc. So let's go ahead and do that with our numbers right now. Not our numbers, excuse me, our letters. So I'm going to solve for Kc, which means I'm going to take Kp and divide it by RT to the delta N. And that's going to give me the value of Kc, isn't it? So what do we know Kp is? We know that Kp from our other page, because this is a continuation of another problem that we just did, is 3.2 times 10 to the 2. Well, what's R? R is 0.08206 liter atmosphere mole Kelvin times T. Well, T from our problem was 1325 Kelvin, right? Times 1325 Kelvin. And I'm going to go ahead and take that to the power of delta N. Well, if you look at your equation, what do you have? You have 4 moles of products minus 1 mole of reactants. So that gives you a delta N of 3. So that means this is going to be the third power. And if you do your math, you come up with, using significant figures, because we have 2 significant figures here, 2.5. I should write this over, sorry. Okay, so I can come up with 2.5 times 10 to the negative 4th. And that's Kc, and that's in terms of molarity. Okay? All right. So you can go back through this podcast. You can look at our problems in class. I've given you some examples in this podcast of different twists, some different ways problems are set up. And if you notice, when do you use ice? You use ice when you have things like into an empty container. After decomposition took place, something was measured. All right? It was allowed to reach equilibrium after equilibrium was reached. Right? There's also the word in here, initially. And that's different than the problems we were doing the other day, or the problems we did earlier in this, right? See, look at this one. Calculate the equilibrium concentration of each species. You don't know it. That's when you use ice. Versus these, right here, what's it say? At equilibrium. What else does this say? At equilibrium. So when things are at equilibrium, you solve them normally, regular, Chem 1 baby. And when things are not at equilibrium, and you need to find information about them, you use ice.